Hi everyone, and welcome to today's webinar hosted by us here at Carmenta Spatial Technologies. I hope you're all having a fantastic day. My name is Thomas Johnson. I'm a software engineer here at Carmenta Spatial Technologies. And joining me today is our very own CTO, Tobias Moberg, as well as a dear colleague of mine, Dr. Mika Ritri. And together we're going to explain to you guys how, using Carmenta Engine, that we can support you when it comes to resupply missions, and the objective of finding the most optimal rendezvous points, friendly link-up, between a mobile supply unit and a mobile frontline unit in the modern-day combat zone, which is an ever-changing battlefield with lots of different threats that we need to take into account when we construct our path planning and mission statements. With that said, I just want to mention a quick few things before we start. This webinar, after it's done, will be recorded and published on our YouTube channel. So if you miss out on anything or want to see something twice, feel free to use this video to rewind and see some of the technical parts again, because it can be a little bit challenging to understand all the technical parts from the first viewing. So feel free to watch as many times as you want. We will have a live Q&A session after this webinar here today. So if you have any questions that come up during this webinar, please feel free to drop them down in our comment section, and we will try and answer them as much as possible. If you have any private questions or further interest in regard to that, please contact us at our support@carmenta.com, and we will gladly share any interest with you guys or answer any further questions. If there's some questions that we couldn't answer during the Q&A, we will try to reach out to you through email as well. And with that said, with that part out of the way, we're going to start this talking a little bit about why we focus so much on resupply missions this year here at Carmenta. Well, everything started on, well, before that, but the initiative was brought up on February 2022 when Russia launched a full-scale invasion of a neighboring European country. It's not far away from where I live. I live in Sweden. And this invasion has still ongoing almost 3 years now, and it shocked the world. It's still a developing story. God bless every soul part of that tragedy. It's still ongoing. But that changed everything, and we learned so much from this war and how it's evolving. At the time, NATO chief Jens Stoltenberg, he was pretty early on in the war, talking about the idea of ammunition and the battle for ammunition between the Russians and the Ukrainians. When it comes to ammunition, there are two very important aspects. The first aspect is the idea of manufacturing large quantities of ammunition with good quality as well, high quantity. But the second part of that one is just as important. That is the supply lines. How do you get this ammunition that is so crucial out to the frontline unit in active combat? It's very crucial, time sensitive. You don't want to run out of supplies in order for you to maintain a front line or push in a counteroffensive and whatnot. So the supply lines are extremely crucial and sometimes underestimated, just like the Russians underestimated it in the beginning. So Ukraine was very successful in fending off the invading Russians at the beginning by targeting the supply lines. So as Ivan was pushing straight for Kiev, the Ukrainians were targeting the supply lines of the fuel supply lines, the ammunition supply lines. So as they were approaching Kiev, they were slowing down rapidly, and in the end they had to retreat. And all of this is because they outran their own supply lines. They're pushing ahead too quickly. So here today, we're going to talk about the supply vehicles as high-value targets. So they will be exposed to a lot of threats. And today, to decide the best rendezvous points, the link-up position, we will take into all the sort of different threats that exist on the battlefield to see if we can minimize exposure to the risk as much as possible, while still maintaining this sensitive time aspect of getting the supplies out to the frontline units so they can keep pushing the initiatives without having to return to base or retreat as a whole. And with that introduction out of the way, I want to hand it over to our very own CTO, Tobias Moberg, who's going to introduce our company here at Carmenta and how you, with Carmenta Engine, our very own product, can solve many difficult tasks of terrain routing.
Hello everyone, and welcome to this Carmenta webinar on risk-adaptive rendezvous planning for resupply missions. My name is Tobias Moberg. I'm the CTO of Carmenta, I want to take a few minutes to introduce Carmenta and the technology that we provide. So Carmenta, we're a pure software company, and we focus on creating geospatial software for mission-critical applications. Our head office is in Gothenburg, Sweden. We've got offices as well in the United States, as well as in Germany, France, and the United Kingdom. And the reason for this is that we like to work really closely together with our customers, ensuring that you get the most out of our products. And the technology that we provide is designed to visualize and analyze geospatial information. And when we talk about geospatial information, we're not only talking about the static data. Of course, you've got your satellite image, you've got your elevation model, you've got your land use classification, and so on, that you want to use in your mapping system. But you've also got all that dynamic information, such as positioned vehicles, or maybe live data coming in from a radar system, or why not a video stream that's being downlinked from a drone and draped on top of the map in real time. Our technology is really good at pulling all that information together and then presenting it in a very effective way, but also performing different kind of analysis on that data to help the end users understand what's going on in the map and how you can operate in your environment. Our technology can be deployed in a range of different ways. You can build web-based solutions running completely inside a web browser with our technology. You can do mobile apps on Android and iOS, as well as traditional applications running on Windows, Linux, and also embedded Linux. So we're very flexible when it comes to how you can integrate this support for visualization and analysis in various types of applications. Looking at some of the key benefits of our technology, well, one very important thing is that we've decided very early on when we started designing the technology that we would not create our own proprietary way of handling information, of storing information. Instead, we've designed the technology so that it can read data from virtually any format. Out of the box, we support more than 100 different data connections, and that includes both traditional file-based data, both civil formats and also military data formats. It includes geospatial databases as well as web service connections. So we're very much data agnostic. It doesn't matter how your data is stored, you can directly use it inside our technology. But as I mentioned before, of course, not everything is about the static geographical data that you want to pull into your solution. It's just as important to be able to pull in that dynamic information that is specific to your application and use case. So we've designed the technology to make it as easy as possible to integrate dynamic data into your solution. There are well-defined programming APIs for integrating everything from positioned objects to live video feeds or other such dynamic data. And finally, another key tenet in how we design our technology is interoperability. As far as possible, we try to always use openly available standardized formats when exchanging data in a web service environment. We've got two main products in our product suite. The Carmenta engine is the core technology we provide, packaged as a sort of toolbox that helps you visualize and analyze geospatial information. And this is a toolbox that's designed from the ground up to be used in mission-critical systems. So it's an extremely reliable technology. It can really handle the requirements in a typical mission-critical system. Performance is another key aspect of the technology. It can handle large amounts of information without slowing down the analysis or the map display. And finally, as I mentioned, openness is very important for us. We strive to be as interoperable as possible with the solutions that we provide. The Carmenta engine is packaged as a so-called SDK, a software development kit. So this is a tool that a system integrator, a developer, can use to integrate functionality into an application. And we provide a wide range of programming APIs to make this as flexible as possible. You can do C++ development with our technology. You can use .NET languages such as C#. There's a Java API, and you can even script the map engine using Python. So regardless of how you do your development, the engine is easy to integrate into your solution. So the other main product in our product suite is the Carmenta server. And the server is a sort of encapsulation of the same core technology. But rather than providing programming APIs, it provides standardized web service access to the same functionality. Carmenta is a proud member of OGC, the Open Geospatial Consortium. And OGC, they standardize ways of exchanging geospatial information in a web service context. And Carmenta Server has certified support for all the important OGC standards, and that ensures that systems built on Carmenta Server are interoperable out of the box. One way to use Carmenta Server is as a centralized way of handling large geospatial datasets. So rather than having to deploy the datasets to each and every client, you put them in a central place, and then you let the clients access that through these service interfaces. But you can, of course, also use Carmenta Server for web-based development. Carmenta Server can be a reliable, high-performance backend for systems running completely in a web browser, for example, using the OpenLayers or Cesium JavaScript libraries. We also support container deployments out of the box. The Carmenta Server core packaging supports both Docker and Podman containers, which can be a very easy way to deploy solutions using Carmenta Server. So that's a quick highlight of the core functionality that we provide. So before I hand over to Gothenburg, I want to give you a little bit of a demo of our core off-road routing capability. And I will do that by switching to one of the demos that are included in the Carmenta Engine SDK. So the application that I opened now is called the Carmenta Explorer. It's included in the SDK as a way of playing around with maps that you've created for Carmenta technology. You can interact with objects, you can enable and disable different map layers and analyses. So the map you see right now, well, right now it's only a satellite image. We're in Northern California, it's Lake Tahoe that you see up here. And you can see I've defined 3 different waypoints in this map. These are waypoints that I want my off-road vehicle to visit. So what kind of data do we need in order to figure out how we can get from A to B to C in this map? Well, of course, we need an elevation model. I'm visualizing that now using a hill shading effect on top of the satellite image. Because, of course, our vehicle will have a maximum slope that it can handle, both going forwards and going sideways. But it's not enough to know the slope, of course. There are many other things that affect whether you can traverse the terrain or not. So another data source that is important is the so-called land use data, or the terrain classification. In this case, for illustrative purposes, I'm using a very low-resolution land use data. But you can see the dark green areas here indicate forests, bright green is open land, purple is waterlogged, and so on. And of course, our vehicle is then modeled in terms of the different types of terrain that it can traverse and at what speeds. Finally, of course, the road network is another important data source, because in most cases you will want to drive on the road rather than on the field next to it. So the vehicle is also modeled in terms of what speeds it can attain on different kinds of roads and bridges and tunnels and so on. So all these different data sources, they come together and create a model of the terrain. And of course, another important input to the calculation that I already touched upon is the vehicle characteristics. So the vehicle model determines the capabilities of the vehicle in terms of how it can traverse different kinds of terrain, what slopes it can handle, whether it's amphibious, and so on and so forth. But given all that data, we can very rapidly figure out how to traverse the terrain in the most efficient way. So the layer I'm now enabling actually shows a suggested route for this type of vehicle to go from A to B to C here. And for each leg of the route, you can see that I'm also displaying the approximate time it will take to go from A to B. And if I start to move this waypoint around, you can see that dynamically the map is updated, the route is updated to reflect the new waypoint. So this is a completely dynamic calculation, taking into account all the dynamic data that can go into the scenario. You can see here that the route that is suggested, it's actually doing a bit of a detour over the field here. And the reason for that is that I've configured this map so that there is an additional input to the calculation in the form of a tactical overlay. So actually, I've got a suspected enemy observer over here, and I've configured the view shed of that observer. That is also calculated on the fly using our technology. I've configured that view shed to be a no-go zone for the vehicle. And that means that if I move this observer up so that it covers the entire field here, the suggested route will do a detour to avoid this no-go zone. And also, you might have information coming in on a tactical data link, for example, that certain areas in the terrain are no-go. There might be suspected IEDs on this stretch of road over here, for example. And then that will also be taken into account dynamically to create a route which avoids that area. This is a completely forbidden area, but the calculation actually also supports areas which are dangerous, but not completely forbidden. And Thomas and Michael will talk more about how these so-called softly restricted areas can be used in the calculations later on. So this example that I showed you right now was an example of how we can calculate a route from A to B to C. But there's another part of this analysis package as well, which can calculate so-called accessibility in terrain. So the layer that I'm enabling right now is showing you so-called isochrones in the terrain. And an isochrone tells you how far you can get in a certain amount of time from a specified start position. So the starting position is over here, and the labels you can see in the map are actually minutes. So in 10 minutes, my vehicle is able to go from here all the way over here, for example. And as we can see, if I move up into steeper terrain here, for example, then it will be much slower going, and I will not be able to reach as many places in those 10, 15, 20 minutes. So this isochrone calculation can give a very good indication on how quickly an object can move from one area to another in the terrain. And you'll see examples of how this can be used also later in the presentation. So that's a quick look at the basic off-road routing capability that is included in Carmenta Engine's SDK. And with that, it's time to hand over to Gothenburg, where Thomas and Michael will talk more about how this functionality can be exploited for the resupply mission use case. Enjoy the show.
Okay, so thanks to Tobias, we now know a little bit about how terrain routing works with Carmenta Engine. Now we're going to contextualize this with respect to resupply missions. So this is built on our paper for GVSETS that was selected this year for 2024. So if you were a part of that, you will recognize these slides. And if it's your first time, if it's your first time, then have a joy. And of course, some of these parts are very technical. So after leave any questions if you have in the comment section. I will try to answer it at the end of this webinar. Otherwise, just rewind the tape when the webinar is over and you can go through them and reach out on our support. But yeah, okay, so we will first describe the problem, the ideal scenario of a resupply missions, and talk about some of the things that you can screw and change in regards to the path planning and stuff like that. So here we have a supply vehicle, or an illustration that I put together. Supply vehicle on the far left, a frontline unit, a mobile frontline unit coming downwards from the right side, the yellow box. We assume this frontline unit to be mobile. It's on a fixed path that has been communicated between it and the supply unit, so it's not very flexible. It's on a fire mission. It's on a shoot and scoot mission, so it's just going on and on. The supply vehicle needs to link up with the with the frontline unit, hand over the supplies. The frontline unit continues its mission while the supply vehicle returns to base. So it follows the black line to link up with the frontline unit at the red spot, which marks the rendezvous point. That has an associated location, geospatial location, as well as a time frame when the frontline unit is expected to arrive there. So it's like a smooth transition in that sense. We have some areas marked on the map as risk zones 1, 2, and 3. We want to avoid these as much as possible. This could be sniper fire, minefields, and other things that could potentially be in there. You know, the battlefield changes every single day, so you need to update new information. Buildings are blown up and bridges are blown up, etc. So it's an ever-changing environment. But in the ideal scenario, we can avoid all the risks, get to the rendezvous point in time, and link up in a smoothly way. Now, what if this is no longer possible for us? We have gained some sort of delays, we underestimated our speeds, or our communication with the frontline unit now. We have gained some sort of delay or misunderstanding of the time frame of linking up with the rendezvous points. One way of still managing going to the same rendezvous point would be to cut corners. So if we can get there a little bit faster by cutting corners and enter risk zone 3, which is shown by this red dashed line, excuse me, we can get to these rendezvous points still in time, but this exposes us some sort of risk inside of this risk zone 3. Could be sniper fire and whatnot. And that's sort of like the first instinctive ideas of rendezvous planning, resupply mission, is understanding the risk zone that you want to avoid and some of them that you might be willing to enter, as long as that they're limited in how exposed you are, and sort of minimizing the amount of time that you spent in there, just like the softly restricted areas that we saw. Now we want to do something a little bit further on with this, and we want to look ahead a little bit on the frontline unit's fire mission, its itinerary that's moving along, and see if we don't really like the initial rendezvous point, what if we scatter multiple rendezvous points along its itinerary, and from all of those possible rendezvous points we can select one, but perhaps a little bit further down the road, where we can cut a little bit shorter time inside of these risk zones, so that we have a smaller overall risk exposure, but we still get in this timely manner to these rendezvous points a little bit further down the road, or further down the itinerary of the frontline unit, and hand over the supplies, mission success, and return to base with a higher success rate of the mission. This raises the first problem, which is, okay, so we go from routing from one point, one starting position, to one rendezvous point. How do we handle multiple rendezvous points without losing massive amount of performance? And to do this, what we instead do is we solve the shortest path problem. We switch the shortest path problem from generating a solution to a tree. So let me explain. The starting position now becomes the origin point in a tree that we expand in all possible directions using Belmont Ford or Dijkstra's. And if we make this tree large enough to cover our operational area, then we can find all of our rendezvous points inside of this tree. So when we have generated this tree, we have already solved all of the rendezvous points, because as long as they exist inside of the tree, we can reverse engineer the path to those rendezvous points. So it's kind of similar to a minimum spanning tree. And you can do this with Command Engine using our isochronic maps, but this is something that we do under the hood. So it's very similar to the isochronic maps, so isochron maps. So let me visualize this more in the context of a mission here. So we have a starting position in the top left corner. We have an AO that we're operating in with some terrain of various sort, different colors. We have a yellow road network here that we can traverse. And we happen to have a destination point in the bottom right corner, also marked by this triangle of blue tail color. And so this shortest path tree would then be represented as an area, so the marked area there in red. And so since we have, this is a much smaller localized isochron, so it's not as big, it's just the surroundings of this starting position. So what essentially means that every single point inside of this red area is accessible to us within some time limit. And if we want to do a routing to any of these points, we've already solved the problem. It exists inside of our tree. So what I was trying to say is, as long as we generate these first initial tree solution to be large enough to cover our AO where we are operating in, we have solved all of the underlying routing problems to all possible rendezvous points. So we don't actually lose that much performance, even if we want to take into account 100 different possible rendezvous points. So that's a very big performance boost. Now, how do we know and select the best rendezvous points? Because we're measuring two different things here. We're measuring time, the time of arrival, and we'll get there in a timely way so that the link up is smooth. We also want to take into account something different, risk exposure, so accumulated risk. And these are two different objectives. And that gets us to the problem of multi-objective optimization, where we're trying to minimize travel time and minimize risk exposure. But these are two different objectives. And a solution to a multi-objective optimization problem is known as a Pareto point, or Pareto route in our case. So these routes are fully legitimate, but they're different in how much time it takes to get to the final destination and how much risk you're exposing yourself. And just briefly mentioning some of the methods that we use here today is linear scalarization method and the epsilon constraint method. So in the linear scalarization method, you essentially associate a scale to each objective function, and you can scale them up and down in importance depending on which of the objective function you want to prioritize. So when you change the scales, you change the solutions. For the epsilon constraint methods, then you focus on one objective function, travel time, and then you put all the other objective functions as constraints. For example, give me the quickest way to my solution, but only expose us to this level of risk. And when we change the risk for higher or lower, we either find a solution or don't find a solution, and it will change depending on the constraints. And this is a graph to illustrate sort of my point here of generating multiple different solutions. So we have accumulated risk in the y-axis and travel time in the x-axis. So here we have 5 different solutions plotted in blue, 1, 2, 3, 4, 5, and they visualize different types of solutions or different type of focus. Solution number 1 is very high on the accumulated risk bar, but it's very low on the travel time. So it's a very quick route, but we're probably going through many threatful areas when we enter it. And solution number 5 is the complete opposite. Here we're minimizing as much risk as possible, but by going around them, then we take a higher travel time. And so in Incrementa Engine, as we saw before by Tobias, we have these softly restricted areas. And depending on how much penalty we want to add to the idea of entering these risk zones, that will give you these different solutions. So we have something in the paper we call the safety value S, which is a value between 1 and 0. So if S equals 1, that means that we take full risk. So we're just going head on, and that would give us possibly solution number 1 in this case. And if we take the safety value as close to 0, minimal risk, then we avoid as many of them as possible, and that would probably lead us to solution number 5. So that's different ways of generating different solutions for each rendezvous point. But that leads us to an even bigger problem, right? So we have hundreds or possibly 100 different rendezvous points that has multiple different solutions depending on if we want to scale up risk or speed. So how do we define the winners for the individual rendezvous points? Well, to do that, we utilize the deadline that is associated with the rendezvous points. So we split all the possible solutions for one rendezvous point into those solutions that gets us there in time, according to the deadline, the link-up time on the rendezvous points, and we call those punctual paths. And all of those possible paths that avoid too much risk, that don't get us there in time, we call those target paths, and they're disqualified. And then we minimize S as much as possible, so that we expose ourselves to as least amounts of risk as possible, until we only have a few valid solutions left. And those rendezvous points that are still valid, those are the left ones that we'll be minimizing further to see which among these leftover rendezvous points is the best one for us, has the least amount of risk exposure. And that's how we pick the winner.
So, hello, I am Mikael Rittri. I will continue with some more details about the algorithm. We can start by defining what is the accumulated risk. Well, let's define it as the travel time spent in risk areas. So that assumes a uniform risk level. Now, how do we find the least risky punctual path? One idea is to use a multi-objective algorithm that will find all paths on the Pareto front. One such is NumMo A*, but that's a slow algorithm. So instead we simplify it to a single objective optimization. We minimize a weighted sum of risk minutes and plane minutes, and then we can use A* when we have a single objective. Okay, that gives only one Pareto optimal path, and it depends on an arbitrary weight we have chosen. So then we repeat that with many different weights. For example, cautious weighting could give us isolines with this slant. Along each line, the paths will be equally good in this weighting. We would find the best path as number 5, which is slow but safe. With a different weighting, we get bold approach, a different slant of the isolines, and the best path found will be number 1, which is fast but risky. We can repeat that with many weights. Can we afford that? Yes. Lisa Lee has found that using A* 200 times with different weights is still 500 times faster than using NumMo A* once. The drawback is that A* doesn't find every path on the Pareto front. It can't. It can only find those on the convex hull. But that should be okay in practice. Still, thanks to having deadlines, we don't have to try 200 different weights for A*. We can bisect the weight interval. We have a weight S that is defined to be in the interval from 0, maximally cautious, to 1, maximally bold. Let's start with S being 0. If we do find a punctual path with this cowardly setting, it must spend 0 time in risky areas, and we can stop with the success. No risk taken, great. But probably we don't find such a safe route. So we try S1 instead. That's the daredevil setting. And even if that setting doesn't find any punctual path, we can stop with failure. But probably we'll find some paths that are punctual but unnecessarily risky. So we'll do a new search with S being a half, trying to find a compromise path that is still punctual. If we succeed, we can try S being 1/4. Otherwise, we can be more bold and try S being 3/4, always bisecting the remaining interval. Then we can stop after, say, 10 iterations, instead of trying 200 iterations. But we have different alternative rendezvous points, and they have different deadlines. But that doesn't matter, because we can exploit that with a single search. We can find paths to many alternative goals in one search operation if we use Dijkstra's algorithm instead of A*. So that's a huge performance benefit. So at each iteration we use the same weight to search for paths to all rendezvous points. We can still use bisection to narrow down the interval. So here is one problem example. We assume that the forests that are green are perfectly safe because you are concealed, while non-forest is uniformly risky. At time 0 we have a supply vehicle at the black diamond to the left. The frontline unit is traveling south and will be at A at 50 minutes and at E at 175 minutes. We have chosen 5 alternative rendezvous points that must be reached within the deadlines. So at the first very cautious iteration, we find 2 perfectly safe paths to A and B, but they are tardy. If we find no paths at all to the other points, so this is too cowardly. If we are maximally bold in the next iteration, it turns out we will exploit roads in some places. We still can't be in time to point A, so we can discard A. We do find punctual paths to the 4 other, with the safest one spending 26 minutes in risk areas. So that may be too bold. Let's try with the S being a half. That reduces the risk to 1 minute and 54 seconds. So let's try to be even more cautious. Now we no longer use the roads. We get down to 6 minutes and 19 seconds. And we try to be even more careful. So this is very low risk paths, but tardy. So that was too cautious. At 3/16 we get one who are still slightly late. Let's be a little more bold. At 7:30 seconds we are punctual with 2 seconds to spare to point B, and we spent 5 minutes and 10 seconds in the risky areas, and that seems hard to improve. So let's stop there. Now you may ask, what if we had more than 5 rendezvous points? Let's say 64. In terms of performance, that's not much worse than just 5. In this example, we measured about 3 seconds of calculations to find 64 black paths, which we can compare to finding the purple path. It takes about 1 second. So yes, we can afford lots of rendezvous points, which gives better flexibility in finding a safe path. Now let's look at some work in progress. We wanted to study what happens if both vehicles are willing to adjust their routes and both willing to wait for the other one. Because in our old problem, the main vehicle was stubborn and didn't budge in their plans. But now let's assume they can cooperate and adjust both routes. That gives us 3 basic formulations. One is that main guy starts from A, supply guy starts from D. They want to meet somewhere, and we want to minimize the time to that place. A second problem statement is that, okay, they want to meet, but the blue guy wants to continue to B, and what's important is to minimize the time to reach B. So that's similar to our older problem. And the most general formulation here would be to say that, okay, blue guy wants to go from A to B, green guy wants to go from D to E. They want to meet at R somewhere, but what we want to minimize is some weighted sum of the arrival times to E and B. So that's what I want to approach here. So we can set up an example where we have A, B, D and E are given as part of the problem. And here I have guessed one R somewhere in the middle. Then I can use existing component we have to calculate travel times. So we can sum those 4 travel times, but we also have to account for the waiting time at R. So we have 5 numbers to sum. Here they are given in seconds. So our component can calculate this in about 1 second. But there are many alternative places for R. So in just the visible part of this map, we have about 800,000 terrain cells. And maybe half of them can't be traveled in. But still, that's 400,000 possible positions. So 1 second for each will take about 4.5 days. So that's not so great. A better way is to use isochrone rasters, because we already know how to compute isochrone rasters efficiently. That's using Dijkstra's algorithm instead of A*. An isochrone raster contains the travel times from some starting point A to all points nearby. So we have used script A for the starting point A. So the corresponding isochrone raster we call ordinary A. Then we have 4 isochrone rasters, A, B, D, and E. And rasters are easy to add. Let us say we want to minimize the sum of the 2 arrival times to B and to E. If we ignore the waiting time first, we can find the arrival time for the blue guy by looking up this in the sum of the blue rasters, A and B. And for any R, we can find the supply time arrival by looking up in the sum of the 2 green rasters. But we must also account for the waiting time at R. So we can find expressions for the waiting time using maximum and subtraction, and get one complicated example for the thing we want to minimize. But we can do some simplification as well. So B plus E plus twice the maximum of A and D is a raster. When we look up R in that raster, we find a prediction of the sum of the 2 arrival times. Let's see that in action. We don't guess an R, we just compute the values for all possible R's. So the brighter colors are better, and the one we guessed in the middle was pretty good, but we have better ones along the roads in the northwest. And this can be calculated in about 2 seconds, so instead of 4.5 days, we have a better prediction time. The question now is, do these predictions agree with the route finding? And here we have moved R to the best predicted position. And the sum of the arrival times agrees with 1 second difference. So that should be okay. In this map we just display the routes, so it's easier to see that the green path goes north and then uses the road westwards, while the blue guy has to go north to reach the roads and then has to go west and back again to use the road network to circle around to get to B from the south. Remaining challenges is that so far we have only used raster isochrones. But our component for isochrones, it only computes rasters off-road. When you're on-road, it will compute line geometries with attributes. And that's to be able to handle bridges and tunnels and ferry routes and so on. So this is not necessary if we only have ground roads with the terrain access, because then the isochrone values on road will agree with the isochrones for the nearby terrain. But for bridges and tunnels and so on, there can be differences. So we would have to implement addition and maximum and so on, also for these vector-based isochrones. And we haven't done that yet. But maybe sometime we will.
Okay, everyone. We have a little bit time left here, so we wanted to dedicate this to a Q&A section. So here we'll try and answer all the questions that will come up during the webinar. But before that, I actually wanted to bring some questions that we received during the GVSETS presentation this year. So part of this material that you saw today actually comes from our GVSETS paper. We were selected this year for 2024. It's our second year at GVSETS. It's a ground vehicle exhibition in Michigan. And yeah, so at GVSETS we met both military personnel as well as professors from various doctor students from various universities across America that had shared interest in this and looked into similar problems of terrain routing and similar stuff with different types of vehicles and such, and the difficulties we share in this domain. So one thing that I wanted to just stress a little bit, so one of the questions that we got was the idea of the convergence rate. So since we talk about the safety value S that basically balances risk and speed, it's a big question since we're bisecting, going half and half. So how long does it take to actually find an optimal solution? Since this is supposed to be an onboard system, well, from our studies, we find that the appropriate convergence time is around 10 to 12 iterations. After those number of iterations, that you get a large enough resolution to where you can really pinpoint the most optimal solution among possible 100 rendezvous points without much performance drop, as long as the rendezvous points are contained geographically in a reasonable area of operations. One thing that could be important to point out is that you should have some upper bound on this convergence rate, because you can end up in a situation where geographically you have two solutions here, one solution here, one solution here, oh, like the camera here, and then you pinpoint it here. So you get this kind of, I call it the triangle of doom. So for one solution it finds no optimal, and then we bisect further, we find two solutions, and then for next iteration, so it can't decide. It can't always decide exactly one solution, because there could be two possible solutions that are very close to one another. So in your algorithmic approach that we've approached it, we can sort of limit that to select multiple solutions, but then present out of those the different types of risks that you're taking on. So it's important that in the scenario we saw today, we only have one type of risk that we really presented. That was the visual exposure, but you can also present it differently to the operator of multiple different risks of the different types that you saw from my illustration early on. And when you're presented with these variations of risks that you're undertaking, one solution might be more comfortable for you than the other. So it's also always possible to select multiple solutions for the operator, and then from those multiple solutions, then you can select some of the best ones among those. So it's more openly in that way, rather than just a strictly best one. But in most cases, we can also pinpoint the best one, if that is what you wish. Yes. Also, another question that we received that we thought was interesting to mention is about uncertainty and the communication between the frontline unit in the supply vehicle, because we know in the modern day combat zone that we don't want to send out too many signals to expose ourselves. Also, there's a lot of jamming going on, as we see from the front lines. So what happens in the uncertainty in the speeds of these vehicles when they're trying to intercept one another, and an uncertainty on the positioning? So what we saw here today is more absolute values when we're looking at the absolute position and the absolute time of arrival. And we have studied this to a limited extension. And what we saw was that, for example, if you have variation in speed, what the algorithm does is it prioritize the rendezvous points that are early on. because later on in the itinerary, the fire mission of the frontline unit, since the uncertainty grows as further away they go, further down the interception, the uncertainty grows so much that we're not really sure if we can intercept at all. So when we take into account uncertainty, there's some later options that are no longer available to us because of these principal uncertainties. So when we apply more uncertainty principles to it, it prioritizes the rendezvous points that are a bit earlier on, a bit closer to the current location of the supply vehicle and the frontline unit. And when it comes to position, we haven't done a lot of that, but you can change the absolute position in the graph of a vehicle to more like an isochrone, so you know sort of where it's moving and where it's dedicated. And the isochrone grows in uncertainty the longer it's been between the communications. But that's something we have studied very limited, but it's an interesting aspect, and we had some cool talks with some of the professors over at GVSETS to talk or study some of this further. But of course, practicality, this is a perfect tool for training, to setting up low-level commands and making these dynamic decisions in the battlefield as is dynamically changing every day. And as Tobias said early on with Comment Engine, it's so easy to add all this dynamic data. As your intel is updated on the fly, you can add in new risk zones, you can change how the road networks look, you can have drones flying over and project that video down, and you can do all that in Comment Engine, and that will update how we see the most appropriate approach to these resupply missions that are very difficult, as I mentioned early on, with these ideas of them being high value targets, so they're very, very sensitive to those risks. But for example, for certain missions, maybe it's better to have an unmanned vehicle versus a manned vehicle, and remote control ones, etc. So it's always up to the operator to make the decisions at the end of the day. But yeah, with all of that said, I hope you have all enjoyed this webinar. I think it has been a great fun for both me and Mikael and Tobias to put this together for you guys. And if you have any other questions or further interest, please reach out to us at support@carmenta.com. That's our email address, and we would love to come by you with some more intel or information and exchange regarding that. But other than that, I hope you guys had a wonderful day and enjoyed this webinar. And yeah, it will be available after this stream goes offline. So if you want to see it again, it should be available for you guys. That said, I want to say bye-bye to you all and have a nice day. And see you guys on the next webinar.